Now it is time for us to take a look of the insert and delete operation. We basically want to do the most basic version of what we call a binary search tree to insert and delete based on the properties of a binary search tree without considering the balanced shape of the tree. There is a special kind of binary search tree which is a subcategory of the binary search tree. Is called AVL tree that is going to take extra care of the balanced shaping of the tree. But like I mentioned, we want to look into the basic form of the binary search tree to do the insert and delete operation. Take a look of this tree so far, saying that we already have 1, 2, 3, 4, 5, 6, 7 nodes inside of the binary search tree, and let us make sure it is a binary search tree. All the left side on the left subtree is smaller, all the right side of the right subtree is larger, and that will also true for node of 5, true for node of 7, true of node of 12. All the leaf node will satisfy those criteria automatically. So saying that based on this tree that we have, first of all, we want to insert the node of 2. Where do you think the node 2 will be inserted? Most of you will probably finding out the right location, which is going to be the left side of node 4. So this is going to be where node 2 it's going to be inserted. Next one, say 9. If I want to insert 9, where am I going to insert it? First of all, you need to understand 9 has to be on the left side of the root because 9 is smaller than 10. If you put anywhere on the right side, it will automatically violate the idea of the binary search tree. Next, think about this. We know we need to look into the left side, and 9 compared with 5, obviously 9 has to be on the right side of 5 because it's larger. So you will look into that one, compare 9 with 7, it has to be on the right side, and therefore this is going to be the right location of the 9. Sounds familiar? That's exactly the search operation basically. The only difference is that when you do search, you want to search for the null location of the element and then put that element that you want to insert into that spot. Take a look of the next insert, 17. Obviously, compare with 10, go to the right, compare with 12, go to the right, compare with 14, go to the right, and you find a null location. So this has to be the right location for node of 17. So basically you can see that it's the search property. Compare with 8, insert 8, go to here, go here, go here, and you will find it's less than the node of 9, so it has to be in this location. Node of 15 has to be in here, node of 1 has to be here, node of 3 has to be here, node of 16. Make sure you see this one correctly, because 16 compared with 10, go here, go here, go here. Now 16 is less than 17, so it has to go to the left side and find the right location over here. This is the insert operation. So it's actually a more advanced version of the search. And let's take a look of the code to see how does all of this happening. So if we want to create an insert operation, there are some special case which is indicating you want to insert the very first node for the binary search tree, and that is actually an easier case. So in the slides, let's talk about the general case scenario. After this topic is done, we will have a lab to work on the binary search tree in the whole coverage. So let's take a look of the general case for the insert operation. Saying I want to insert a node. This 4th line is the preparation. You should be very familiar with the first line, new node. So you want to create a new node, and now this node has 1 data part and 2 pointer part, which is the left subtree and the right subtree. We want to remember that location by using a new PTR to remember the address of the new node that we just created. Then we put the element into the data part, and we put both left and the right subtree into null, indicating that there is no left and there's no right. When you try to insert a new node, obviously this node is going to be a leaf node, so that we would naturally to put the left subtree to null, right subtree to null. So that's the preparation work. We create a spot, then we try to look for the right location for us to insert. This one is a little bit more special because you can see we're creating 2 pointers now. The first node will equal to root, so now that's where we are able to start searching. The second pointer is the parent node of the node that we want to search. Because think about this, we will keep search until P or the node equals to null, indicating that is the space we want to search. But for the binary search tree or the linked list implementation, we can only go forward, we cannot go back. So instead of going back, we simply use a parent node that will follow wherever the node that we travel, and we remember where is the parent of that node. That's why we will have 2 pointers to help us. While P is moving to the next location, parent will stay on the previous one. Then when P moves to the next one, parent will go to where P was originally at. So they will move simultaneously. Always look for the new location which expecting to hit a null location, while parent will stay at the parent row. So in the loop that we're trying to do, as long as it's not null, that means we need to keep moving. Okay, and then P to the data is not equal to the element. This is going to be a special check for us to see if we have a duplication of the value. As long as they hit a null, it will stop the loop. As long as they find the duplication, it will stop the loop, saying that there is a special scenario. So this whole process is trying to help us finding the right location. And you can see that if then the search operation happens, if element is less than P to the data, what we want to do is we make parent remember this location, and then P will move to the left side because element is less than P to the data. If it is greater than the data, P will still stay at the parent location, and then P will move to the right side. So we will let them keep moving until P hits a null spot, ideally for us to find the right location to do the insert. So saying that if P equal to null, which is exactly the things that we are expecting, otherwise that means there is a duplication. So we will say the duplication is there and then end the program. So if P is equal to null, all we need to do is try to link the parent with the new pointer. So that you can see if element is less than P to the data, then we just say P parent to the left equal to the pointer. So we link that one to the parent. And otherwise we link to the parent's right child. And that is how we will be able to do the insert operation. Of course, let's take a look of an example to see what's happening over here. Saying that this is the tree that we have and we want to insert 10. Obviously, you know 10 will go all the way over here, insert to the right child of 9. So let's take a look what's happening. In the beginning, the first 4 lines of the code will give us a space. And then try to remember that as a new PTR, put 10 over here, null and null for both child. So now it is time for us to trace the whole process until we find the right spot. So you can see that in the beginning, parent equal to null, P equal to root. So you can see P is the same location of the root, parent is null. Now let's try to see what's happening over here. Since P is not equal to null, P is equal to the root, and P to the data is not equal to element. 5 is not equal to 10, so we will need to search. Since element 10 is greater than the data, so this is a false statement, and we will come to the true statement. We need to travel to the right side. So you can see what's happening over here is that we will travel to the right side, indicating that P will comes to the next location while parent will still remember the original location. So now parent at the location of the root, P is at the next element. The loop will coming back. P is not equal to null. P has a location, and P to the data 10 is not equal to 8. So we're good. We can continue search. So again, we will see the element, which is 10, is not less than 8. So we will come to the else part. P will move to the next location. Before we move that, we need to make parent equals to P. So you can see parent is at this location, P is at this location. Come back over here, do it one more time, compare P is not null. It has an address of this element. Data 9 is not equal to 10, so we will keep moving. So before we move P to the right side, which is going to be a null, we try to remember parent equals to P, so that we will see parent is at this address, P is a null location. Now, since P is null, we will stop the whole while loop and let us prepare to link this element with this element. Now, finally, we compare, try to see that this element is actually greater than the parent node. So we obviously need to link this right child to the new node. So we go into say P to the parent to the right, which is this box over here, equals to new PTR's location. And that is going to help us insert the item. That's basically the insert operation. Delete is probably the most complicated one because there are 3 scenarios. You may ask, why 3 scenarios? What are those scenarios? This need to come back to the basic property of the binary tree. Because when you try to delete a node, there are 3 possibilities. This node is a leaf node. That's the first case scenario. This node has 1 child. This is case 2 scenario. Obviously, you may guess the case 3 scenario is this node has 2 children. A good example usually is the case of the root or any other nodes that have 2 children. So we need to think about how do we handle all of these 3 scenarios. Look into the first case scenario on the side, you will understand this is actually the easiest case. If this is case 1, indicating that this node has no child at all, then we can simply delete this node. If this is not the case, that indicating that the node has 1 child, either the left side or the right side, what we will need to do is that we need to take this node away and then hook up the whole subtree into this spot. So it will end up with like this. If we take a look of example, saying that we want to delete node 5. When we delete node 5, the whole subtree is here, then we need to link 10, the root, to the left node to the whole subtree over here. That's the idea. And I want you to think in computer point of view. Node 10 has a left child, point at the address of this node that we want to do the deletion. The whole subtree is actually stored at the address of right side of node 5. So we need to make this connection happen so that we will end up with this subtree, this binary search tree. In another example, I say I want to delete node 14, the whole subtree need to come up over here and then hook it up, indicating that that's how we will be able to do the case 2 scenario. How about case number 3? This is actually a more complicated one. So let's come back over here, saying that using this tree, after the 2 deletions of the case 2, say I want to do the deletion of node 10. This obviously is going to be more complicated. So how do we do that? How do we delete node 10 and then still make the whole thing stays as the binary search tree. To get the answer out of it, you need to understand one thing. Node 10 has 2 children. All of the nodes on the left side is smaller than node 10. All of the elements on the right side is greater than node 10. So, to find a right point to satisfy this location, you actually have 2 choices. Since all of the nodes on the left side is smaller, as long as we find the maximum on the left side to go over here, then we satisfy the condition. On the other side, we can also find the minimum on the right subtree because all of these are greater than this one. The minimum on the right subtree is smaller than all of these as well. So the finding maximum and finding minimum are very useful in our case 3 deletion. So you can see that when we try to delete a node that has 2 children, there are 2 choices. You can find the maximum on the left side or the minimum on the right side to look into to substitute that location and then delete the node. And that's the idea of how we would be able to do the case 3 scenario. Sounds a little bit complicated, right? Let's take a look of another example. Say now we want to use the minimum on the right side. When we try to delete node 5, we need to come into here, try to find the minimum. So where is the minimum? We will travel from the root of this right subtree, go to left side, finding out 6 has no element on the left side. So 6 must be the minimum of the right subtree. So what we would do is that we would delete node 6, put 6 over here, and then when we do the delete of node 6, we will trigger, in this case, a case 2 scenario, so 8 will need to link with 7. Notice this. When we try to find a substitution, we will only end up with case 1 and case 2 deletion, because it cannot be case 3 if it is case 3. That means it has both left and right child, then it cannot be minimum or maximum. Because the definition of minimum is there, you keep tracking until you find a node that has no left child. And it cannot be the case 3 deletion. And that is the important observation in our case 3 deletion. So to take a look of how do we do deletion in program, this is what we will do. First of all, you need to find the element, and doing so is actually using the same technique that we have when we do the insert. We need to find the element first. Not only we need to find the element, we still need to remember who's the parent of that element we want to do the deletion, so that we can bypass that and then link to the child of that. And therefore, you can see that to do the deletion, we need to have using p equals to the root, parent equal to null. While p is not equal to null and p to the data is not an element, then we will keep tracking, go to the left side or go to the right side. While we move, we will still have the parent, remember, with the parent of the next node. So we would need to do the same operation about the insert until we find it. There are 3 cases. The first case is that for the node that we want to do the deletion, the left side is null, the right side is null. So that's our case 1 scenario. So when that is happening, all we need to do is that we simply go back to the parent, finding out this is the left side that we are talking, the left child, or this is the right child, and we just say the left child is null if the element is less than parent to the data. If otherwise, then we just say parent to the right side equal to null, so that we would close the node that we want to do the deletion. And basically, free the space as the last step that we need to do. This is our case 1 scenario. So you can see that if we keep moving roots starting from here, we find, say, delete 4, we will be able to find the node of P in here, parent at node of 3. Since this is a node that has no left child, no right child, all we need to do is that we just say, because compare with this node 4 with the node parent's data, we understand the right side of the child has to be null. So we just say null over here, free the space, and that would end up with our case 1 scenario. For case 2 scenario, there are 2 possibilities. Either the node you want to do the deletion has a left child, or the node you want to do the deletion has a right child. So saying that if the left child is the case, all we need to do is that we need to bypass that element, make parent to the left. If the element is less than parent to the data, that means it's going to be the left side of the parent, then parent to the left will equals to the node, the child's address. So it will be P to the left because it is the case that left side have the child. If that's the other case, element is less than parent to the data, then parent to the right will equals to P to the left. That's under the situation that the node you want to delete has a left child. Otherwise, if the node you want to do the deletion has a right child, so what you will need to do is that make the parent try to find out is going to be the left side of the parent or right side of the parent, and then bypass that goes to P to the right child. Let's take a look of an example over here. Saying that this is the tree that we have and we want to do the delete 9. So we will go over here, travel all the way down, finding P is at this location, parent is at this location. So in this situation, P has 1 child, which has 1 right child. This is the second case too. When that is happening, what we want to do is that we want to make the parent, because it's the right child, P is the right child of the parent, we want to make parent to the right, we want to make parent to the right equals to P to the right child. So that when that's happening, you will have formed a link point the address at the element of 10. So that is what's happening in the case 2 scenario for the deletion. Finally, if we are looking at the case 3 scenario, it's actually easier because you have already taken care of case 1 and case 2. For case 3 scenario, it's one step of the recursive function. What I'm trying to say is, first of all, we try to create a variable to store the minimum value of the right side. Once we get it, all we need to do is remove that element from the tree. This recursive function will take care of case 1 and case 2 by removing that element. And then we change P to the data, the element's data equals to that minimum value. And that's it, as simple as that. So you can see that, saying that we want to delete a node of 3, what's happening is that we would have a P point at this location, parent point at the previous location. So what we want to do is that we want to find the minimum of the right child. For this one, P to the right, so since there's only one element, you will find this element over here. When we try to do that, we will do remove element of 4. So this whole tree will go to this process, remove the element of 4. In this case, it's the case 1 deletion. And then we simply say that this data equals to the value of 4. And we will end up with this case 3 deletion. That would be also true when you try to remove the root. So finally, this topic tells you that the binary search tree, in terms of search, insert and delete, all of them require the search operation. So if the tree is in a good shape, everything is fast. All of these will finish in a log n operation. However, if the tree is in ugly shape, which means that it's basically a linked list, then everything would be slow. And therefore, the performance of the binary search tree relies on the shape of the tree.